Welcome to topology class. Today we will discuss about continuous functions. Last class too we have discussed about continuous function, that is the function continuous at a point. Today we will discuss about a continuous function, that means a function which is continuous in the entire domain. First of all we are having the definition. Let f from x to y be a function and script t and u be topologies on x and y respectively. Then f is said to be continuous, or we will say that tu continuous if it is continuous at each point of x. And in the previous class we have discussed what is continuous at a point. What was that? In order to prove the continuity, from previous class we are having the idea, if this is my xt and this is my yu, then a function is defined from x to y. We will say that this is continuous if at a point x0, what we are going to do is we will find f of x0 and find an open set which containing this f of x0. Then we can find an open set over here such that which containing x0. In topological terms we will write if there exists a v belongs to u open such that f of x0 belongs to v, then there should exist some u belongs to t such that x0 belongs to u, and condition is f of u is contained in v. This is the condition. If such a thing is existing, means we will say that the function is continuous at x0. Now here, if this condition is existing at all points of your domain, then we will say that the function is continuous. Now we are having a theorem, 3.4 theorem. Let xt and yu be topological spaces and f from x to y a function a function. Then the following statements are equivalent. Then the following statements are equivalent. First statement is f is continuous. Second statement, for all v belongs to u, f inverse of v belongs to t. Third one, there exists a subbase. There exists a subbase S for u such that f inverse of v belongs to t for all v belongs to S. For all v belongs to S. Fourth one, for any closed subset, for any closed subset A of y, any closed subset A of y, f inverse of A is closed in X. And fifth one, for all A subset of X, f of A closure is contained in f of A all closure. So these are the equivalence conditions for a function to be continuous. Now we will prove one by one equivalence conditions. So first we will assume that condition 1 and we will prove condition 2, that is f is continuous, then for all v belongs to u, f inverse of v belongs to uh, the topology T that we want to prove. Or else if v is an open set, then its inverse image is also an open set that we are going to prove. So proof, one implies that we will prove. Assume f is continuous, f is continuous at each point of X, and V is an open subset of Y. Now if X naught belongs to F inverse of V, then F of X naught belongs to V, right? So what do we want to assume? If you took an open set, so this is the thing you want to prove. You are having x2, x2, and this is yu. You take here an open set, this V, then go for its inverse image. Okay, suppose here. Now this is your F inverse of V. We want to prove that this F inverse of V is open. Okay, so we assume that F is continuous at each point of X and V is an open subset of Y, right? Now if X naught belongs to F inverse of V, that means here we are having a member X naught, then f of x naught will be inside this. What's the reason? Since we are assumed that f is continuous. Since f is continuous means we are having uh, f of u is contained in v, right? So that's why we're having f of x naught belongs to v. But then v is a neighborhood of f of x naught, right? Then v is a neighborhood of f of x naught. And so by continuity of x naught, and so by continuity of f at x naught, what you will get? F inverse of v is a neighborhood of x naught. It's a neighborhood of x naught. Thus, f inverse of v is a neighborhood of each of its points. Each of its points, right? And so is an open set in X. So is an open set in X. Okay. What is having? We have assumed that F is continuous, and we want to prove that if you are having a V open in Y, then its inverse image is also open in X. So first we are assume that F is continuous at each points of X. Now you took an open set V in Y. Now the first thing is that if x naught belongs to f inverse of V, then f of x naught belongs to V. If this is the condition, means V is an open set we have taken and f of x naught belongs to V, then this V is a neighborhood of f of x naught, and at the point x naught, f is continuous. Then by using the continuity definition that we have studied in your previous class, we will get there exists an open set in X such that x naught belongs to that open set U, and that f of U is contained in V, right? So we will have this f inverse of V is a neighborhood of x naught. Thus, f inverse of V is a neighborhood of each of its points. Since we have taken x naught as an arbitrary point, this f inverse of V should be a neighborhood of each of its points. And so, it's an open set in X. So, we have proved the first part. Now, we will prove 2 implies 1. 2 implies 1. That means we want to prove f is continuous. So let x naught belongs to x. Given any open set V, given any open set V containing f of x naught and f inverse of V is an open set containing x naught and moreover f of f inverse of V is contained in V, which implies your f is continuous at x naught. See, we want to prove f is continuous, and what we want to assume? We want to assume the condition 2. Condition 2 was for all V belongs to U, f inverse of V belongs to tau. That means we are having an open set in Y, then f inverse of that open set is in X tau, right? So we have assumed the second condition, x naught belongs to X given any open set V containing f of x naught, then f inverse of V is an open set containing x naught. If that is the condition, then f of f inverse of V should be contained in V. So this together implies the continuity of f, which implies f is continuous at x naught. Next we will prove 2 implies 3. 2 implies 3. What is 2? Can we get directly? Because 2 says that for all V belongs to U, f inverse of V belongs to T. Now there exists a subbase S for U such that f inverse of V is belongs to our topology tau for all V belongs to S. So it follows very easily, right? Since for any set this is true, so in particular for a subbase element also it is true. So that part is very easy, trivial one. So 2 clearly implies 3. Now we want to prove the converse, that is 3 implies 2. Now 3 implies 2. We note that the inverse image preserves intersection and unions. That is, the meaning is that if you're finding f inverse of v1 union v2, then it's nothing but f inverse of v1 union f inverse of v2. The same way intersection also, right? So We note that the inverse image preserves intersection and unions. Now let V belongs to U. Then V can be written as union I belongs to I of Vi, where Vi is our base elements, right? Where I is an index set, where I is an indexed set, and for each I, Vi can be written as the intersection of finitely many members finitely many members of S. Finitely many members of S. Say S1I intersection S2I intersection etc. intersection SRI of some I, where Ri belongs to M and Sji belongs to S for 1 less than or equal to J less than or equal to Ri. Can you follow this? See, what you have assumed is condition 3 you have assumed. Condition 3 means there exists a subbase S for U such that F inverse of V belongs to T for all V belongs to S. And we want to prove that for all V belongs to U, F inverse of V belongs to T. So you have assumed that there exists a subbase. And what you're going to do is this is your xt and this is your yu. Okay, now let V belongs to U. Okay, so here we are having an open set, that is here. Suppose I am taking this as my open set, so this is my V. Then we are assumed that there is a subbase, right? And this has got a base, so V I can write it as union of some base elements, right? So I belongs to I. I'm taking that base elements as Vi. Here the notation, yeah, Vi. So Vi are going to be my base elements, right? Vi base elements. And you know what's the definition of base and subbase? For subbase means intersection of subbase is S is equal to, I'm taking as S1, S2, etc. Some Sn means I can write this V1 as intersection of some S1 intersection, S2 intersection, S3 intersection, some S4 intersection, extra intersection, some SKs. By definition, the intersection of subbase elements should form the base element. So each of this Vi, okay, each of this Vi can have a subbase form like this. Okay, that means I can replace this with this. That only we have written here. See, Vi, each Vi can be written as the intersection of finitely many members of S. That is, since we are using Vi notation, this I will represent these are subbase elements for Vi. That's why I have put this I. Okay. Now up to Ra elements we are using. I think you follow it. Then if you're finding F inverse of Sji, F inverse of Sji. Now this belongs to our topology T. Each of these members, right? But the topology is closed under finite intersections. Finite intersections. And so F inverse of Vi belongs to the topology. Right? So have you got this one? F inverse of Sji. So in order to find F inverse of Vi, I should have F inverse of, see, right here. So now I am having my V equal to union I belongs to I of Vi. Therefore, F inverse of V equal to union of F inverse of Vi. I can write I belongs to I, right? But each of this F inverse of Vi or Vi is intersection of this type. So this is equal to union I belongs to I of, I can write F inverse of each Vi is of this type, right? So S1I intersection, S2I intersection, etc. intersection, SRI of I. Then again, your F inverse commutes with intersection we have take. So this is union of I belongs to I of, I will get this as intersection I equal to 1 to Ri, right? S Si of or Sj of I. This I am putting as J. So Sj of I. Now this is the thing we have written. See, F inverse of Sji. Oh, I have missed here. This is F inverse. So F inverse of Sji. That means this quantity belongs to your topology top. Now topology is closed under finite intersection. Therefore, this quantity intersection J equal to 1 to Ri, F inverse of Sji also belongs to a topology. Then again, it is closed under arbitrary union. So union of this is again closed. That means You are having F inverse of V belongs to your topology. So F inverse of Vi belongs to the topology. Next we will prove 2 implies 4 and 4 implies 2. These two facts follows from inverse image preserves complements. So which follows from the fact that the inverse image preserves complements. Inverse image preserves complements. That is, for any B uh, set of U, F inverse of uh, Y minus B is equal to X minus F inverse of B. Okay, so this is the F inverse of Y minus B is X minus F inverse of B. So this is the meaning of inverse image preserves complements. Now 2 implies 4. Now we can get from this 2 to 4. 2 to 4 we want to go. Now for all V belongs to U, F inverse of V belongs to T. Now for any closed subset A of Y, F inverse of A is closed in X, right? Exactly the complement. So it will can be easily proved using this complement idea. Okay, now we will move to 5 implies and implied by 1. 5 implies and implied by 1. Once you prove this, we will get all the equivalence conditions. Now for this, suppose for all A belongs to X, F of A closure is contained in F of A whole closure. Now we have already proved this in a when you're taking F at a single point. We can prove similarly. So proceed as in proposition 3.2, where you proved 3 implies 1 also. Okay, so we can easily prove this. Just you refer the previous proposition. In that we have proved this 3 implies 1 and 1 implies 3 and all. Okay, so just you have that idea and try to complete the proof. Next we are having one more proposition. 3.5 proposition. Composition of functions are continuous. Composition of continuous functions are continuous. Composition of continuous functions are continuous. That is, f from x to y comma g from y to z are functions with f continuous at x naught and g continuous at f of x naught, then G composition F is continuous at x naught. This we have already studied in a real analysis class, so I'm not going to the proof of this. Next we are having a note. Any function from a discrete space and any function into an indiscrete space is continuous. Its meaning is that suppose you are having a function from x to y. So in order to make this function continuous, just you want to take here if you are having the discrete topology where discrete topology in your domain, then f is continuous, or we can make it continuous in another way as to take x and y, f from x to y. Now here in the codomain, if you are having indiscrete topology, then also your function should be continuous. So in topology, it's very easy to define a continuous function. You take in the domain discrete topology, then any function is going to be continuous, or in the codomain you take indiscrete topology, in that case also the function should be continuous. That is, if T and U are topologies on a set X, then the identity function I from x to x is TU continuous if and only if the topology T is stronger than this topology U. Okay, so what it says is, generally we will say that identity function is always continuous, but in topology we can have non-continuous identity function also. Okay, so this is x and this is also x. Now from x to x I am having the identity function. Now suppose here I have got a topology T and here I have got a topology U. Then in order to make this I continuous, I continuous, but the condition is here the topology that I define should be stronger than the topology here. That is implies this T is stronger than U, right? That's the meaning. See, if T and U are topologies on a set X, then the identity function I from X to X is tau U continuous if and only if the topology T is stronger than U. So, if you want to have a discontinuous identity function, it's very easy to define. From X to X, you define the function, identity function, and put some topology in this domain, which is weaker than the topology over the codomain. Then your function cannot be a continuous one. So, hope you understood today's section. I'm winding up today's session here. Thank you for your patient listening. Thank you.